перевести на русский. Значит, уважаемые члены Совета, вы ознакомлены с повесткой дня. Сегодня у нас основной вопрос – это защита диссертации доктора Нагин. Название диссертации представлено вот здесь, на подсказке, и это защита проводится человеку, который является профессором университета. Сейчас давайте разберемся. Из Египетского центра теоретической физики, и он прикомандирован к Институту ядерной физики нашей академии. Значит, официальными оппонентами являются профессора Рустам Ибадов, Мухайо Расулов и Виктор Михайлович Чудаков. Так что здесь порядок производный оппонентов. Значит, вот здесь есть у нас список документов. Вот, с ними ознакомит нас Караман. Пожалуйста.
Представленные представительные документы полностью соответствуют положению ВАК Республики Узбекистан. В частности, здесь имеются положительные отзывы от всех официальных оппонентов и ведущей организации, а также выписки протоколов заседания семинара, проведенного в Институте ядерной физики, и семинара по теоретической физике при нашем спецсовете. Материал данной диссертации был размещен на сайтах Национального университета, Института ядерной физики и Астрономического института Академии наук, а также на сайте ЗИОНЕТ. По теме диссертации Савика были опубликованы 24 научных работ, из них 23 в лицензируемых журналах. Сейчас я зачитаю вам характеристику на Савика, которая дана руководителем Института ядерной физики. Birinchi 967 yilda Misrning Sohat shahrida tug'ilgan, Germaniya fuqarosi, ma'lumoti oliy. 1989 yilda Asyut universiteti bakalavriatini, 1993 yilda Asyut universiteti magistraturasini bitirgan va O'zbekiston Respublikasi Fanlar akademiyasi Yadro fizikasi institutiga hamkorlikda ilmiy ishlar bajarish uchun qabul qilingan Abdulnasir Tavfiqqa tavsifnoma. Abdulnasir Tavfiq o'zining ilmiy faoliyatini 1993 yildan Germaniyaning Marburg universiteti aspiranti sifatida boshlagan. U 1999 yilda nomzodlik dissertatsiyasini himoya qildi va Marburg universiteti tomonidan fan nomzodi ilmiy darajasi berildi. Shundan so'ng Tavfiq Germaniyaning bir nechta universitetlari fizika fakultetlarida ilmiy xodim lavozimida izlanishlar olib bordi. Shu jumladan 1999 yildan 2000 yilgacha Lenin universiteti ilmiy xodimi, 2000 yildan 2002 yilgacha Stuttgart universiteti ilmiy xodimi va 2002 yildan 2005 yilgacha Viktor universiteti ilmiy xodimi lavozimida o'z ilmiy tadqiqot faoliyatini davom ettirdi. O'z tajribasini orttirish va ilmiy saviyasini oshirish maqsadida u 2005-2006 yillarda Yaponiyaning Hiroshima universitetiga ilmiy xodim sifatida ishga qabul qilindi. Tavfiq 2006 yilda Qohira shahrining zamonaviy texnika va axborot texnologiyalari universitetiga ishga qabul qilindi va 2007 yilda bu professor unvoniga sazovor bo'ldi. 2007 yildan to hozirgi kungacha u Qohira shahrining zamonaviy texnika va axborot texnologiyalari universiteti qoshida Misr nazariy fizika markazining direktori lavozimida ishlab kelyapti. Tavfiq olim va mutaxassis sifatida o'z oldiga qo'ygan ko'plab ilmiy muammolarni muvaffaqiyatli va ijobiy hal qiladi. U fizik tadqiqotchi sifatida o'z bilimlarini oshirish maqsadida tinimsiz izlanishlar olib bormoqda. Misr nazariy fizika markazining direktori lavozimida ishlayotganiga qaramasdan u o'rgangan ilmiy mavzular bo'yicha ko'plab maqolalar chop etgan va anjumanlarda o'z ma'ruzalari bilan qatnashgan. Hamkasblar bilan munosabati juda yaxshi, o'ziga yarasha obro' e'tiborga sazovor inson. U O'zbekiston Fanlar akademiyasi Fanlar yadro fizikasi instituti bilan 67 12 rakamli Birleşken Ruhsatlar Kengişliğe takdim ediş için verildi. Институт директора Скайфлай. Если обращение получит диссертацию диссертанта, в адрес спецсовета не поступило.
Спасибо. Так, что за следующее? Так. Ну, прежде чем дать слово доктору Тафику, я хотел бы сказать, что эта диссертация, она прошла два семинара, и очень детальное рассмотрение было сделано нашими рецензентами при обсуждении этой диссертации. И в результате этих обсуждений доктор Тафик переделал значительно свою работу, были добавлены новые публикации, которые были опубликованы на протяжении этих последних лет. И в результате мы видим итог его работы над диссертацией, когда в результате замечаний он был вынужден еще 2 года ее дорабатывать. Значит, и сейчас я предоставлю слово доктору. Dr. Please go ahead and you have 20 minutes for your talk.
Good minutes. 40 minutes. 40? But only 40.
Okay, 40.
40.
Okay. Yeah, people agree.
Okay. Yeah, okay. They agree. I also have to. Okay. Yeah, thank you very much. I have the pleasure to be here, but also I'm very honored to stand in the front of this council. The title of the dissertation is the Transport Properties of TGP and the Implication of on Early Universe. Here is the agenda of the talk. I will start with motivations, then I will give a short review of the state of art on research on the subject, the implication on early universe, some results, and I will list my publication, and I will show new direction in this research and the outlook. The motivations are manifold. One of them is the CMP, the Cosmic Microwave Background Radiation observations confirmed the hot origin of the universe. From this data, we know that the distribution of matter is homogeneous and isotropic. From the CMP spectrum, the CMP spectrum shows that this matter was in thermal equilibrium. And the data we have here can be taken from this cube and WMAP and the Planck satellites. The motivations regarding the cosmic equilibrium, if we have a thermal equilibrium, it means the interaction rate exceeds the expansion rate of the universe. The expansion rate of the universe was slowing down with increasing the co-moving time or the cosmic time of the universe. Increasing the cosmic time brings particle species closer to thermal equilibrium. If the expansion is an adiabatic one, means no heat flow or absorption took place, thermal reversibility of expansion and contraction, no entropy change. The fluid of the background, the fluid filling the background geometry can be ideal or viscous fluid. If it is an ideal gaseous fluid, it means no interaction, at least no long-range ones, take place. It means the inertial energy doesn't depend on the volume occupied. If it is a viscous fluid, it means we have the velocity gradient, we have long-range correlations, and we have the viscosity coefficient depends on the energy density. All these are motivation for my work. We know that the relativistic cosmic cosmology requires cosmological principle and general relativity besides the equation of states. If we write the metric in this form, where t is a moving time, the cosmological principle requires homogeneity and isotropy at least in large scale geometry. In spherical coordinates, the Friedmann-Lemaitre-Robertson-Walker metric describes the cosmological principle. If we consider the energy momentum tensor in this form, for example, this is for perfect background matter, and we connect all this together with the Einstein field equation. We connect the geometry with the matter here, then the Friedman-Robertson volumetric, Friedman-Robertson Volta metric, and the energy momentum tensor in the field equation leads to the famous Friedman solution. Background matter, and we connect all this together with the Einstein field equation. We connect the geometry with the matter here, then the Friedman-Robertson volumetric, Friedman-Robertson Volta metric, and the energy momentum tensor in the field equation leads to the famous Friedman solution. In general, I can say that we need equation of the state in order to solve the Friedman equation. The thermodynamics and even the cosmological parameters of early universe are dictated by which form has the energy or matter filling the background geometry. It depends on the matter. What we have right now from the relativistic Heavy-Ion Collider and the Large Hadron Collider results on the QGB gives hints on the equation of the states. Also, we have hints from the lattice QCD simulation. We have experiments, Heavy-Ion collision experiments, for example, LHC, and we have hints about the equation of the state describing the QGB. We have sophisticated studies in lattice QCD, and we know exactly how it looks like the equation of the state. Based on this information, we can try to solve the Friedman equation. For example, the first one, this one here, can be solved depending on the equation of the state describing the energy density here, where K is the curvature parameter, can be negative or positive 1, also can be 0, it can be vanishing. When K is plus, it means we have positive curvature and we have finite size. When K is 0, we have flat universe, and the background can be described by radiation. When K is negative, it means negative curvature, infinite size, maybe hyperbolic geometry. Where the energy density can be related to the scale factor here. I'm sorry, the screen is too long, but it means rho is proportional to A to 4 and A to 3, and A proportional to rho itself, depends on the values of this curvature. The Friedman equation can only be solved if we know the equation of the state, for example, this one. Here you see different graphs, or graph describing the scale factor as a function of temperature depending on the equation of the state. If we have radiation, we have this behavior. If we have matter, we have this green line. For this de Sitter space, we have this blue line. And for expanding space, we have, where omega is minus 1/3, we have this purple line. Here is the same, but for the Hubble parameter, we can do the same. I mean, depending on the equation of the state, we can solve the Friedman equation, and we can describe the universe. The equation of the states. I mentioned that we have a lot of information about the equation of the state. For example, lattice QCD. Sorry. The lattice QCD here. Here is the graph between the temperature and the chemical potential, which can be related to the center of mass energy. Here we're supposed to have the quark gluon plasma, and here we have a lot of information about the equation of the state. For example, lattice QCD. Sorry. The lattice QCD here. Here is the graph between the temperature and the chemical potential, which can be related to the center of mass energy. Here we're supposed to have the quark gluon plasma, and here we have a Hall phase. The lattice QCD results show that going down from QGB to hadrons, you have to go through a phase transition. Here, the phase transition is a crossover. Had centered a certain critical temperature, at least at mu equal to 0, about 170 MeV or 160 MeV. The critical temperature decreases when you increase the chemical potential. At large chemical potential, we have an endpoint. This endpoint is a second order. It's connecting the first order line here, this green line, with the crossover line. All this information, we know that we can, going from hadron to quark-gluon plasma, we can describe very well the thermodynamics. Even the freeze-out curve, which here I'm drawing here, the temperature as a function of chemical potential. Here I'm collecting a lot of data, experimental data, starting from SIS experiments, which has about a couple GeV to AGS, SPS, REC, and even LHC. All these data can be described very well using one universal condition. Here I'm suggesting that the entropy normalized to T cube is just a constant, and we can describe very well the chemical freeze-out. The chemical freeze-out is the information about the critical temperature and the chemical potential at which there is no production of particle. I mean, the chemical reaction is in equilibrium. We have, as I said, we have here from experiment, we have here from lattice QCD, then we know very well how it looks like the equation state. Again, the lattice QCD can give us a bit of information about the thermodynamics. For example, here the energy density normalized to T to 4 as a function of T over Tc. We are moving from hadrons here to the quark-gluon plasma at higher temperature, yeah, but we still, even if we have temperature 3 times Tc, we still below the Stefan-Boltzmann limit. This has an indication that the QGP is not an ideal gas. It should be some other form of matter, maybe fluid, maybe viscous fluid, or maybe fluid with strong correlation. The same here can be seen if we study the pressure normalized over T4 as a function of the temperature. The different curves here are depending or are drawn at different quark flavors. Here, for example, the purple one for pure gate theory, where the critical temperature is about 270 MeV. If we have here 4 QCD, 2 flavor, 2 plus 1 flavor, and 3 flavors, we have different critical temperature, but all of them are around 200 MeV. Means now we know exactly that at about 200 MeV, the matter goes from hadron to quark-gluon plasma and vice versa. We can study the behavior here using an effective model, for example, the hadron resonance gas model. I'm showing here the critical temperature in sigma squared, in the square root of sigma. Square root of sigma is a parameter in lattice QCD, has the value of 420 MeV as a function of the pion mass here, also in the square root of sigma. The red line draws the SU3 gate theory. As I said, the critical temperature has 270, where the lightest particle is the gluon or glow ball, has the mass of 1.4. If we go to full QCD, the lightest particle is a pion. If we use 144 pions, the critical temperature about 180, 190, depends on how fine is your lattice. I said that the critical temperature has 270, where the lightest particle is the gluon or glow ball, has the mass of 1.4. If we go to full QCD, the lightest particle is a pion. If we use 144 pions, the critical temperature about 180, 190, depends on how fine is your lattice. We can compare this using the resonance gas. The advantage of using resonance gas is that we can describe the degrees of freedom when we go from hadrons to the quark-gluon plasma, and this can be seen here through this nice fitting of the lattice data through these curves, which are from the hadron resonance gas. Doing this or having this, we can also study other sophisticated parameters, for example, the correlations and fluctuations. We can study the particle number, for example, here for different particle species here, kaons, pions, and even omegas, and we can describe them using the hadron resonance gas at a huge range of square root as a center of mass energy. We can describe this very well. For example, the correlations and fluctuations. We can study the particle number, for example, here for different particle species here, kaons, pions, and even omegas, and we can describe them using the hadron resonance gas at a huge range of square root as a center of mass energy. We can describe this very well. Means using the resonance gas, we can have a command on describing the multiplicity. We can study the fluctuations using these dynamical fluctuations, for example, here. And here I'm showing here results of kaon over pine, strange kaon over light pines here, at different parameters of gammas here. In doing that, in order to describe this behavior very well, I have invented a method in which I'm assuming that the distribution function of T has a non-equilibrium form. When I do this, I can describe very well this kind of time when I have here a jump, sudden jump at a certain energy here. This energy corresponds to the SPS energy. Having the experimental data, for example, for matter antimatter here, I think is anti-bind over bind. From SIS, EGS, REG, and even NHC here, ALICE data, we can very well describe the data using the resonance gas, where when increasing the energy here, the energy increases here up to several thousand GeV here, we go to the value of 100%. It means the quantity of matter and antimatter are almost equal if you have very high energy like here, but if you go down to a lower energy, we have almost matter. We don't have antimatter. This is a reflection of how can we use the experiment in order to describe the early universe. The early universe corresponds to this high energy here, where the matter and antimatter are almost equal. This I have done for proton anti-proton, but I have done also for kaon anti-kaon, as to show you that even the strange particle ratio behaves similar. This has been published in this year. The same, at very high energy, the kaon anti-kaon are almost equal, reflecting the situation at early universe. Now we can go back to the equation of the state. From the lattice QCD, we have pressure. We have pressure here as a function of energy density. I can fit the data very well. The dots are the lattice QCD data, and the curves or the lines are fitting. There is a dip here. This dip corresponds to the phase transition from hadrons here to quark gluon plasma here. It means from this graph we have a relation between the pressure and energy density. We can also have another relation between the temperature and the energy density. Using the latest data here, we can fit it very nicely, and we can describe the situation from hadrons to the QGP. Very nice. Even we can study the speed of sound. Here the lattice resonance with speed of sound, and here the resonance gas in the hadronic phase. It's normal that the resonance gas describes only the hadronic phase. This fit gives us a relation for describing the speed of sound, which gives us an essential information about the equation of the state itself. The discrepancy between the hadron resonance gas and the lattice data, at least below TC, is under debate. Recently, the recent data, lattice data goes up here, maybe reaches the resonance gas curve. This has been published in this year. From REC, we have the elliptic flow. This is an important aspect in order to understand the behavior of matter at very high temperature here. Here we have the anisotropy parameter V2 as a function of data goes up here, maybe reaches the resonance gas curve. This has been published in this year. From REC, we have the elliptic flow. This is an important aspect in order to understand the behavior of matter at very high temperature here. Here we have the anisotropy parameter V2 as a function of the transverse momentum for different particles here, and the curves are the Hadron models. Yeah. The best fit is obtained when we assume that the viscosity is very small or almost vanishing. Therefore, people in 2012, people announced the discovery of QGB based on this graph. Also, we can study the V2 as a function, normalized to the image density as a function of dN over dy. While with the entropy here, we can have this universal graph. The viscosity has been studied also in lattice QCD. Here is the eta over S. Eta is the bulk viscosity normalized to the entropy for different materials here, maybe water, hydrogen. For the QGB, we have this red line which has almost zero viscosity. When we study the eta over S as a function of temperature, here we get this lower band PSS lower band, and we have here this lower band eta over S should be larger or equal to 1 over 4pi. Now we have information about the viscosity itself, and we know how looks like the electric flow of experimental data. We know the equation of the state. We can put all these together in the Friedman equation, and we can describe the universe. This is the motivation of the data, of the whole work. Implication on early inverse, what we need a basic assumption of the cosmological standard. For example, it's homogeneous, isotropic. We need here the Friedman metric. We need the Einstein gravitational field equation, an intermomental tensor, yeah, and we need also a theory describing the background geometry. This can be the fluid in the background geometry. This can be Eckhart theory. This can be Israel Stewart theory. I'm using both theories here. We need also, as I was describing, we need a barotropic relation for the pressure, for the temperature, for relaxation time, and even for viscosity. Barotropic, I mean this quantity has to be expressed in function of energy density. The energy density is easier to deal with because the Hubble parameter can be related to the energy density directly. When we do this, we can directly apply the equation of the state in the Friedman solution. Here, just a result here of the Hubble parameter as a function of t, where I assumed here constant viscosity. I mean, alpha here is a relation between pressure and the energy density. P equals alpha rho. When I assume that alpha is constant, goes from 0.25 to 0.75, we have here different graphs here. Even the zero viscosity, we have it here. It means when you put viscosity, even with small value, you will affect the evolution of essential cosmological parameters, as you see here. It doesn't depend on the value of viscosity. Which value you are using, you have change. You have essential change here. Here, another result here, where I'm using here finite cosmological parameter, finite cosmological constant here. This should be this purple line. This red line is the ideal fluid, and this line without cosmological constant here. While we have here this negative t, it is not a physical description here. But we got it. We don't have singularity if we don't use finite cosmological constant. But if you use it, we can get concept comparable to the ideal one, where we have zero viscosity here. The same can be done using the Israeli Stewart theory here, where again here the red line is the ideal case. The blue line without cosmological constant, and the purple line with cosmological constant. Means also the cosmological constant can affect or have an effect on the evolution of, in this case, the Hubble parameter. Here is a comparison between the Hubble parameter here in physical units here and the co-moving time in physical units. This paper has been published in this year. Here I'm comparing between the ideal case and when we got viscosity, finite viscosity on X. Here I'm listing the publications. Here you can see that I have publication on early universe and its implication, and also I have publication on the Higgs collisions here. So, for example, here this one I have shown you this matter-antimatter asymmetry Higgs collisions. This goes to the quark-hadron phase transition in the early universe. This Hubble parameter again, the anti-proton to proton ratio in Alice experiment I have those published last year. Again, Hubble parameter. We go back to the dynamical fluctuations of K to pi and back to the early universe. Again, matter-antimatter asymmetry, viscous quark column plasma in the early universe. It's better for all of them. I think are goes on early universe physics. A medium multiplication of Hubble properties is an essential parameter which we can also take into consideration when we study the early universe. We can study, here is the latest study on screening mass on thermal and dense medium. Universal description for the freeze-out, I have shown you this graph when I assume that the whole experimental result can be described by just one condition. Entropy over T cubed equals the constant, in this case 7. Particle ratio Higgs collision, quark anti-quark in hadronic phase. This can be used in order to see the phase transition can be mass on thermal and dense medium. Universal description for the freeze-out, I have shown you this graph when I assume that the whole experimental result can be described by just one condition. Entropy over T cubed equals the constant, in this case 7. Particle ratio Higgs collision, quark anti-quark in hadronic phase. This can be used in order to see the phase transition can depends on whether you are using or you are having a light quark or you have to include even the strange quarks. The QCD phase diagram has been published in the Physical Review D. I give here a sophisticated study on the phase diagram of the QCD. The condition driving the chemical freeze-out again. I'm not going to give introduction on all these people on this paper, but you can see I have two legs. One leg on Higgs experiments and the other one on the cosmology. Again, this is the whole list here. New direction. Doing this. People show their interest to include me in the editorial board of the International Journal of Political Physics, Theoretical and Mathematical Physics. Also to include me in the new journal, Australian Journal Physics International. This is recently. Also Springer is thinking about early universe review as a new paper, as a new journal. Being an expertise in Higgs collision and also also work in cosmology or astrophysics motivated Alice at LHC to include us as a member, associate member, and to work in the cosmology and astrophysics and its relation with the Higgs collisions. We have also started last year a conference on the QCD matter in HC era, and this conference is going to be serious. Next year we will have another one. Here is a poster of the next year conference, which will take place, will be held from 10th to 14th February 2017. All of you are invited to participate in. Last year we have had 170 participants from all over the world. We were discussing the two subjects, Higgs collisions and the early universe. Outlook. We need to study, or I think we need to study carefully the cosmological consequence of all what I have done in this thesis. We need to study, to include the matter, antimatter, or even dark matter in it. I just included the cosmological parameter. but we need, or I'm thinking to need the dark matter and being antimatter. We need to study it prior to the QCD era, electroweak era, or even inflation. We need also, or we can think of later on eras, for example, the hadronic era, maybe the Big Bang nuclear synthesis era. We need to, I'm thinking to study carefully quark models and its influence on the strong fields, for example, with a magnetic or gravitational field, with a positive or negative gravitational field. The anisotropic, inhomogeneous. Up to now, I'm assuming that the universe is isotropic and homogeneous. What if it is anisotropic or inhomogeneous? How can we study it? We need also to study carefully the hydrodynamic approaches. I have mentioned two theories describing the hydrodynamics. The Eckart theory, the statistical hydrodynamic, and even the Stewart. Maybe we can think of Lambda theory on other theories, but as you know, the hydrodynamic codes are very complicated, or even if you want to study it in full geometry, I mean in four dimensions. I'd like to study also fluctuation in the Big Bang nuclear synthesis, and even in the CMP era. Yeah, thank you. Thank you.
We have some scientific questions and I have some formal questions. So from which to start? Because here what we did, let me start from formal questions. You see, we look to the list of your publications and the list of publications which were included in your author referral, and plus to your dissertation. And what we have found that 9 papers which were published in Physical Review D and in very serious journals as in Progress of Theoretical Physics in 2011 and 2012 were not included to your dissertation. What was the reason for doing it?
Because I have submitted the electronic dissertation 1 year ago at least, and since 1 year I didn't improve it. I mean, I have a new publication almost every month. Yeah, I didn't include everything. I couldn't include everything.
Okay, I don't know. This was my question, because with results everything is okay, but there is some inconsistency with your presentation and with also referat and dissertation.
Yeah, as I said, I have almost I have new publications. Yeah. And the status of my publications submitted in the thesis are a couple months ago. Yeah? The new publication this month, or even in previous months.
There is some inconsistency with your presentation and with also referat and dissertation.
Yeah, as I said, I have almost I have new publications. Yeah. And the status of my publications submitted in the thesis are a couple months ago. Yeah? The new publication this month, or even in previous months, I didn't include them. Yeah.
Okay, I thank you for your answer. And other question, because you see, when you consider the cosmological model, yes, for example, Friedman model, we assume that it is homogeneous and isotropic. So it means that, for example, when we consider the homogeneous and isotropic cosmological model, we exclude even heat flow, because heat flow will create your inhomogeneity and anisotropy. And my question, you included viscosity. How inclusion of viscosity compatible with the homogeneous, and will it create some inconsistency with the Friedman model? It is my question.
Yeah, it is a very good question. Yeah. I'm just considering the bulk of viscosity. I didn't talk about the shared viscosity. The bulk viscosity is even there if you have a homogeneous and isotopic evolution of the universe.
Еще вопросы, more questions? If I am right, you want to explain universe expansion without singularity. Yes?
Can your theory explain the universe expansion with acceleration?
Yes, it can describe the acceleration as I have shown you.
Singularity. Yes? Without can your theory explain the universe expansion with acceleration?
Yes, it can describe the acceleration as I have shown you. The Hubble parameter is also increasing, and the scale factor is increasing. The problem with the singularity, it depends on the equation of the state. When I used all the equation of the state, which exclude almost everything, I got non-singular behavior. But when I improved the equation of the state, I included much recent ones. I included, for example, the cosmological constant. I got the singularity. I mean, the singularity is there, or it disappears, depends on the equation of the state. The other point is that the equation of the state which I'm using is limited to the QGB era in the early universe. I cannot apply it to the inflation era, for example. I'm not assuming that it is applicable during the Big Bang. It just describes a concrete era, the QGB era, and the description cannot be distributed all over the whole evolution of the universe. If you are restricted to the QGB era, the evolution is this. But if you go back to the Big Bang, maybe you get or you don't get singularity. But this is not a theory. This is not my theory that I don't have singularity. I'm just claiming that I'm describing one era. It's about 1 microsecond after the Big Bang. Yeah. In the time before this era, we have a huge dynamics in the early universe, which I cannot describe, and I'm not claiming that I can describe using this equation system.
Okay, what about the universe acceleration?
The acceleration, yeah, it can be also included, or I can obtain it if I put cosmological constant, if I put even dark matter, dark energy. But up to now, I'm excluded all these. I'm just concentrated on the matter, which is QGB matter. If I include other forms of matter, maybe I will get accelerated expansion.
Okay. Next question, please.
My question is continuation of this one. What the time beginning Big Bang explosion before, during in singularity, the singularity? What do you mean the time beginning from then? The expansion of university becomes non-singular. Beginning Big Bang explosion before, during in singularity, the singularity. What do you mean the time beginning from then? The expansion of university becomes non-singular.
The time scale in which, maybe I can show you a graph here because I have it here. Here, the time scale in which I am claiming that my study is valid is limited to this one. T equals to point scale in which, maybe I can show you a graph here because I have it here. Here, the time scale in which I am claiming that my study is valid is limited to this one. T equals to 0.2 GeV means the time has this value up to temperature of 1 GeV, the time has this value. I'm limited to this time, to this era. Before this, I have no access. After this, I am claiming that I have also no access. I mean, the study is valid within this time period.
So far as I know, the extension of university becomes non-singularity up to after 10 minus 44 seconds.
Yeah, sure. Yeah.
This is
Yeah.
your question is based on this
Sure.
type?
Yeah. Again.
Let's simply give a number for this time given in GeV.
In the second minus.
In second.
Yes.
This should be, sorry. This should be 10 to minus 5 seconds.
Minus 5?
Yeah, 10 to minus 5. Yeah, about 1 microsecond. We're talking about
In this case, you does not mean about singularity
Yeah, sure, I'm saying.
during before Big Bang explosion.
Так, давайте вы задавайте вопросы, комментарии потом.
Комментарий я просто спрашиваю, но он имеет в виду, что действительно после этого.
Okay, shall we continue during discussion? The next question, I don't know. Пожалуйста.
Sorry. As I understand, the important part is your report was devoted to the molasses or viscosity of your plasma. You consider this plasma as some type of molasses. What is the chemical or physical mechanism of this viscosity, of this friction, different part of your plasma? Thank you.
Yeah, viscosity is a bulk viscosity. It comes from the expansion. It comes from that the volume is increasing here.
Yes. And what the mechanism?
Mechanism inside it, we don't know exactly. We have to wait for the LHC experiment. For example, for the lattice QCD.
I understand.
The lattice QCD now is designed to study the transport properties of the QGB exactly. We don't know exactly the heat conductivity. We don't know exactly the electrical conductivity of the QGB. We don't know exactly the viscosity, which mechanism. We don't know exactly. We have to wait for LHC.
Okay, more questions?
You see, you don't consider this dark matter part, and if we assume that dark matter consists from weakly interacting massive particles, how this viscosity model will change the dark matter? So can you include this viscosity and find something from this? Because you have viscosity for particles, and then for dark matter you will have the same viscosity model.
This my plan in future in order to include this part of material. How would it affect the evolution? I can guess just now. I didn't study it yet. I can guess that the expansion will be accelerated, for example. I can guess maybe the expansion goes through differently from the ideal case. I didn't study it yet. It is complicated, as you know, to include the viscosity of this dark matter, for example. Up to now, I'm using just normal matter.
More questions? No questions? Okay, I have almost the same questions concern that curve that you showed, that your result important between these two moments of time. Right? Yeah, it means that there is a different solution given here. What's the difference between these solutions presented here that with different colors?
Yeah, here is a parameter alpha, which connects the pressure with the energy density. It's equation of state. When I assume here, for example, P equals alpha rho, I get this dotted line. When I increase the alpha, and alpha is related to the viscosity.
Oh, okay.
When I increase the viscosity, I get slower evolution here. Yeah. If I remove the viscosity, I get this solid line.
Okay. It means that you have never specific idea about the equation of state. You mentioned that it is very important to have to know that what equation of state. That is the first remark. Second, there is a very difficult problem related chemical potential to density. There is no clear correspondence. You have to solve full QCD, in fact, to have that relation. That's second remark. Third remark, you mentioned that you are able to solve lattice QCD in non-zero chemical potential. That is possible only with very strong assumptions. That is the third remark. And with these three problems which is unclear how to solve, nevertheless, you make very specific conclusions. That is the fourth remark.
Fine. This is very good remarks. First, that we don't have an accurate equation of state. This is correct. We don't have it. It depends on our assumptions. Yeah. We are using lattice QCD at finite chemical potential. In doing this, we have to assume, for example, Taylor expansion, or use the solution of lattice QCD at zero chemical potential and try to expand it or to extend it to finite chemical potential. But as far as I know, the lattice people are very confident that their results can be believed. I mean, the result at finite chemical potential can be compared with the experiment. Lattice itself is a kind of an experiment now, because of its accuracy, its accuracy. Because we have compared it with the experiment, we are using lattice as an experiment. The relation between the energy and chemical potential, right? You are right. We don't have a direct relation, but we are using the chemical freeze out, which we can measure in the experiment, and we know the energy at this experiment, and we can draw the chemical potential in an indirect way. We use thermal models, for example, in order to reduce bulk production in certain experiment, and in order to do this, we have to have finite chemical potential. Then we assume a finite chemical potential. We know the energy density, the energy of the experiment. Then we get a relation. The relation is an empirical relation. It is not a theory. We don't have a theory relating the center of mass energy with the chemical potential. Right. It is a phenomenology.
So, more questions? Okay, thank you very much. So now we are continuing discussion of situation. Now первое продолжаем обсуждение. И вот здесь есть у нас отзывы на you may take a seat.
I take it.
Так, у нас нету отзывов на автореферат. Это сегодня официально отзывом ведущей организации, да? Имеется отзыв. Читайте. Я думаю, что достаточно будет читать замечания.
Спецсовет поступил отзыв ведущей организации Астрономического института Академии наук, составленный ведущим научным сотрудником, доктором физмат-наук Скуропуловым. Этот отзыв был одобрен на заседании ученого совета института 17